So if we are capturing coordinates manually, either by digitizing on screen or digitizing on a digitizing tablet with a puck, we really have to be aware of some concerns. And some of these concerns are unavoidable, but we can mitigate the effect of these by by considering some things. So here's kind of the main idea here. Let's say we were digitizing a 1 to 24,000 map, and we were trying as hard as we could to digitize exactly where a point on that map was, but let's say we were off by 1 millimeter, which is not much. That's a tenth of a centimeter. Maybe your pinky nail is about a centimeter wide, so that would be 1/10 of that width. You could be off by that much just doing your best to digitize. On a 1 to 24,000 map, that would mean you were off by 79 feet in the real world. And that's a pretty significant amount, 79 feet or 24 meters. But if you were digitizing a 1 to a million map, let's say a continental map or something like that, and you were off by the same 1 millimeter, now you would be off by 1,000 meters or more than half a mile, 3,281 feet. And these sorts of errors happen no matter how careful we are about trying to digitize right on top of where that point is on the map. Our hand might just shake a little, or some people's eyesight might be better than others. This shows a study that Bostad did that shows how far off points were, even if people were trying their hardest to digitize exactly where that point was on the map. And we can this just shows how far they were off in the x direction. So they could have also been off in the y direction, which would mean it would be even more. But we can see that even trying very hard, the digitized points were easily off by a 2/10 of a millimeter, and sometimes getting close to 3/10 of a millimeter. So these errors are going to be in our map. And so points are not always going to fall exactly where we hope they will when we click on that digitizing puck or when we click on our mouse as we're doing on-screen digitizing. But that's kind of a fact of life. But what we can do is we can make sure that we don't, that what we're digitizing is what we're intending to digitize. And that has to do with where we put in our nodes and vertices. So nodes are where lines begin if we're digitizing lines, or it's the beginning and ending of a polygon. And so the nodes in this example here are shown as open circles. Vertices are where we do a little change in direction. So with a vertice, we're trying to approximate a smooth line with a bunch of linear line segments. And so each of these vertices in the simple map is represented by a black dot. And what we can see here is that we have 6 different lines represented here. Each of those lines has a node at its beginning and a node at its end. And of course, the intention here is, for example, for this node to fall at the end of line number 1, the beginning of line number 3, but also the beginning of line number 2. And we can see that throughout. 2 different lines are always sharing the nodes, except for the ends that are only one node. But any place else on the map, here and here and here, we always have at least 2 lines coming together at the same node. And this would be great, right, if we're making a map of streets or something else, because we do want to show that sort of connectivity. We want where 2 streets intersect to be 1 point in space, not 2 different points in space. But if we were digitizing, let's say we scanned in an old map and we were digitizing this by hand, some errors might occur. And all of these typical errors are shown in this figure here. So what are some of the errors here? Let's just kind of not be concerned with these label points. This would just be where a polygon is labeled. Each polygon should have a label point. There's one missing here, so that would be one error. But let's take a look at these nodes here and what all of this is indicating. So when this person was digitizing here, they did not intend to put in their last node up here. They actually just intended this line to stop when it intersected this line here. But they did not, they just clicked a little bit off. So now we have this thing that's called overshoot. And here's another overshoot over here, although it's not labeled. And what we say about that last node there, this node and this node, is that it would be a dangling node. We would just like to chop that thing off here and chop that off there and just not even have to deal with those overshoots and dangling nodes. On the opposite side, when this person was digitizing this line here, they did not click close enough to this line here, and so their last node falls short of reaching this line here where it was intended to end. This is something that's called an undershoot, and it's also it also resulted from just this heads-up digitizing, this on-screen digitizing, or digitizing on a digitizing tablet with a puck, and just being a little off on where their locations were. So we're going to talk more about these undershoots and overshoots. This pseudo node here just means there's no need for that node to be there. It was just entered by accident, perhaps. This line is not changing direction here. We don't even need a vertice here, really. We do need a vertice here because direction is changing, but this is all a straight line here. We don't need a node or a vertice here, so we could get rid of that pseudo node. And then when lines cross, there should be a node, but in this case, there is not, so that would also be an error. Someone should have just clicked again here, and that did not happen. So one way we can deal with these undershoots and overshoots is that we can enter a snap tolerance. And the snap tolerance is a distance that you can enter while you're digitizing. And what it says is that, and you can set this for snapping to points or snapping to lines or snapping to polygons, but what it says is if you click here and there is a feature within that snap tolerance, like this line here, then that node is automatically going to snap to the closest point on this line, as we can see over on the right-hand side here. This one does not, because the line and this other point are beyond the snap tolerance. These two lines here should be connected. They are within each other's snap tolerance, and so they will be connected. This works with undershoots, as we see in this example here, but it also works with overshoots. If our node here is entered, that's our last node, and it's within the snap tolerance of this line, it's not going to put that node out here. It's going to put it back onto the line, and that's what's shown on this example on the right here.